All right. Well, I will try to be quick so you can get to the person you're actually here to see. I'm Sarah Pooley. I'm currently the president of the Materials Science Club here on campus, and I'm just briefly talking about some of the scholarship opportunities that are here through the club. A few of which are highlighted on the screen here. If you use the QR codes, you can find out how to apply for these. One of the way you get eligibility for these scholarships is by participating in the chapter and in the parent program that we are a chapter of, which is Materials Advantage, which offers you discounted student memberships to a number of professional societies in materials science. And again, without beating a point about the head, it does offer you eligibility for a number of scholarships that we wanted to highlight here. As for activities on campus, we run a handful of events throughout the semester, mainly to socialize and share opportunities on campus. For example, which labs happen to be hiring for undergrads, of which is the one that I am a part of, which is the Electrochemical Energy Materials Lab. In brief, reach out to us if you're interested in any of these opportunities. Thank you for your time, and I'll turn it over to the person you're actually here to hear speak. Thank you.
All right. You can hear me now, right? Good. All right. So thanks, Elton, for that introduction. I am Marla Dowell. I joined the EDGE Consortium in March of this year, and prior to that, I was working at NIST, the National Institute of Standards and Technology. How many people have heard of NIST? Right. Good. Mostly. All right. Well, let's go back here. So I want to talk about a little bit about the EDGE Consortium. I'm going to talk to you a little bit about disciplinary literacy and what we're trying to do in EDGE to help prepare students from a wide range of STEM disciplines for the semiconductor industry, which is a very interdisciplinary industry. And then I'm going to talk a little bit of career advice about how to look for a job, maybe how to apply for grad school. That was sort of the topics that Sierra asked me to talk about. So this is a little bit of a mashup, but hopefully there's something for everybody here. And the reason why EDGE was stood up was to prepare students for opportunities in the semiconductor industry. With the passage of the CHIPS and Science Act, that created $52 billion of funding to help the US semiconductor industry. And with that, create a lot of future job opportunities. Throughout my career at NIST, I actually spent a lot of time working with students from universities and graduate students and helping them connect to industry jobs. And while I was there, I noticed this real disconnect between how in universities we prepare our students and what I was hearing from my industry colleagues about what they were looking for in their future employees. And so that's what we're trying to fill in that gap, working with schools across EDGE. It's really great that Boise State is a member of EDGE. It's a great example of a school that's already working very closely with industry. We want to capture the successes here, share it throughout the consortium and with other schools around the country. So what is the urgency and the opportunity? The urgency is that this report from the Semiconductor Industry Association said that by 2030, the US demand for STEM professionals is going to be 3.85 million job openings created, with about 1.4 going unfulfilled, with our graduation rates projected today. And then specifically in the semiconductor workforce industry, they're projecting 67,000 jobs going unfulfilled. I'm not dumb. I have two students who are in graduate school right now who've been looking for jobs also. So I know that there is a disconnect, right, between all these job openings that industry says they're looking for, and how do we connect students with those opportunities and prepare them for those opportunities, because that's the big challenge here. And part of the way that we're thinking about this a little differently, and I want to introduce this topic to you and think about this throughout this talk, is the idea of the semiconductor nanotechnology manufacturing competency model. This is how industry thinks about preparing their employees and what the skill sets they are looking for in their workforce. And I want you to look, let's see. Yeah, here we go. look at this sort of whole stack of competencies that they're looking for. Academic competencies is certainly one of them, and that's something that you're learning today at Boise State. But they're also looking for competencies in personal effectiveness, workplace competencies like working in a project team, and then there are some industry-wide technical competencies and industry-specific technical competencies that they're looking for also. Like the previous speaker mentioned, clubs like those student clubs are great places to learn some of these other workplace and personal effectiveness competencies. So I encourage you to take advantage of those opportunities. And the great thing about Boise State is you have Micron nearby and a very vibrant industry environment. So this is places where you can gain some of those industry-specific skill sets as well. But today I'm going to talk about some of the programming that we're developing at Edge to take those competencies and take that knowledge and share that with students who maybe are not in places where they have a fab in their backyard. So I'm going to talk today and kind of broke it up into 3 topics. The first one is Edge and our Edge Scholars Program. And I know that a number of students at Boise State are already part of our Edge Scholars Program. Then I'm going to give you a little bit of background information because I get a lot of questions about CHIPS, the CHIPS and Science Act. NIST is the organization that oversees the CHIPS and Science Act. There's been a lot of news about changes about the CHIPS for America program, and I can answer some of those questions, but also give you a couple of examples from my own personal experience about how interdisciplinary background and thinking beyond just your academic competencies is something that you need to bring to work with industry and to solve industry problems. And then I've got some career advice for students because as the mom of 2 recent college graduates, I can't pass up an opportunity to provide unsolicited advice to students. Okay, so EDGE is about expanding dynamic growth in engineering. It's a national alliance of leading research universities and engineering schools dedicated to transforming semiconductor-related education and workforce development by aligning our academic programs with industry needs. It's led by Dartmouth and Indiana University, but other universities that are involved are Rochester, Brown, Washington, Boise State, Iowa, Berkeley, Olin, Prairie View A&M, and San Jose State University. All these programs have semiconductor certificates of one kind or another, but here's the interesting thing that I've learned over the last 6 months. Guess what? It's all a little bit different, okay? And that's okay. There are no good or bad programs. They're all different, but learning that material and bringing it to the industry and knowing how to apply the knowledge that you're gaining from your education here is the trick that we're trying to help students with to sort of enhance and amplify the programming that you already have available here at Boise State. So part of our EDGE advantage is bringing together sort of all these best practices. There are a number of workforce funding opportunities, seats at the table where people are talking about how we're changing workforce training for this industry at a national level. And by having a consortium of universities, when we show up at the table, guess what? They listen to us, which is really great. But we also have some student-specific programming, and you can see sort of the distribution here. We currently have over 500 students signed up, including students from Boise State, ranging from first-year undergraduate students all the way through graduate students. If you're not signed up for the EDGE programming, I encourage you to do so that you can have access to some of the supplemental experiences that we're offering. Our EDGE Scholars Program is sort of that EDGE is our flagship initiative working with students. We provide externships. We've done 6 trips bringing students to visit different companies over a few days. They get to meet sometimes with HR professionals, sometimes even do interviews. They get to go into clean rooms. It's a really great experience. And so far, we've been able to cover all the costs associated for that so that there is no financial barrier for students participating in that. This fall, we're offering a near-peer mentoring program for students who are signed up for our program. I'll tell a little bit more about that. And we try and highlight opportunities to gain hands-on learning experiences for students. Our goal here is to provide students with access and exposure to real-world industry problems and to make programming that we develop scalable and accessible across institutions. We're actively seeking industry partners to host scholar visits. So if you have a company that you know that would be interested in hosting scholars, please reach out to me. And we have some new schools lined up who will be joining us this fall. Our Edge Scholars learner progression is around building interest and awareness for early career students in the sort of first 2 years of college, then moving them to awareness and investment through programs like the near peer mentoring program that we'll be offering this year, and the visits to companies, and a Chip Kids Ambassadors program that we're piloting at a couple of schools. And then going from there, moving from investment to action, we want to connect students to experiential learning opportunities through internships and then potentially Chip Kids Ambassador leadership programs. I mentioned the near peer mentoring model. This is really an interesting pilot that we're doing with a startup out of the University of California, Berkeley, who's developed an AI platform to match students with near peer mentors who have similar competencies and background and help students explore different career opportunities. This AI tool walks students through a self-assessment of what their competencies are, what their academic background is, and then we'll match them with a near peer. So how many people know about near peer mentoring? Only Eric, a couple. The reason why near peer mentoring is so valuable is, guess what? My experience from having looked for a job as an undergraduate 30 years ago is not as relevant to the students of today, right? So it's better for you to be engaging, even if you're in graduate school, with a near peer mentor, somebody who is a few years ahead of you to provide advice or feedback on classes, potentially on jobs to think about, career opportunities and stuff like that. So with this program, we're going to be giving students both an opportunity to be a mentor and a mentee, and an opportunity to actually gain some competencies around being a mentor and a mentee. And guess what? In that semiconductor manufacturing competency model that I showed of, guess what's a competency in there? Mentoring. Okay, so you get to, it turns out it's very important for an industry is to have people who know how to be good mentors. So I encourage you, if you've been active in our Edge programming before, is to keep an eye out for when we announce the first cohort of students. We're going to be offering this opportunity to up to 1,000 students across the consortium. So that gives you kind of a highlight, a high-level view of Edge and our Edge programming, and a preview of what we're doing. I'd like to take a step back and talk a little bit about the CHIPS and Science Act, and my own career at NIST, about why some of these other competencies beyond your academic competencies are so important if you're working in an industry environment. And why so the CHIPS and Science Act was passed in 2022, and the goal was to set aside appropriations, $52 billion, to reshore US semiconductor manufacturing. This is actually really impressive. There have been 4 big bets that the United States has placed on science throughout history. The first big bet was on the hydrogen bomb during World War II, with the goal of ending the war. The second one was putting a man on the moon in the 60s. The third one was the Human Genome Project, and the fourth one is around semiconductor manufacturing. And the reason for doing this is actually the semiconductor industry was invented in the United States. Ironically, who wants to guess where the semiconductor industry started? Bell Labs. Okay, so somebody got it right. It was actually New Jersey, not California. But where the major manufacturing happened was in Silicon Valley. And part of that is because where the R&D is happening, that's where the industry will go. And in the 60s, we had a very vibrant semiconductor industry in the United States. But today, only 12% of semiconductors are actually manufactured in the United States compared to 37% in 1990. And the hardware accounts for only 3% of venture funding. The reason why this is so important is if we're not investing in those companies, then those companies don't happen in the United States. And we need them because, as many of us experienced during the pandemic, if something broke that relied on electronics, it was expensive to fix. My stove broke. I mean, other people's cars broke. And there are some things you can get around with or get away with not having, like a stove for a couple of months, but some things that you cannot. So the US decided that it was both an economic and a national security issue to reshore the manufacturing to the United States. So when they passed the CHIPS and Science Act, it set aside $52 billion. $2 billion went to DoD, the Department of State, NSF, and Treasury. And then the other $50 billion went to NIST and the Department of Commerce. And that amount of money was divided into two big buckets. One bucket was $39 billion for incentives. And I think you guys are probably familiar with that because some of those incentives came to Boise and is why Micron is building two new fab facilities here and creating a number of new jobs. There are other investments in Arizona, Texas, New York, California, Oregon, Washington, a lot of other companies to build their facilities as well. The other component is the $11 billion for R&D, and that was the part of the program that I was working with. The incentive side was the near term. How do we get some of this manufacturing back into the United States? But if you think about that innovation ecosystem and keeping it here and keeping the US in a advanced at the forefront of semiconductor manufacturing, then we need to have that research and development piece as well. And that research and development piece, they created 4 programs. One program was the National Semiconductor Technology Center, which you may have seen about in the news recently. And that was the majority of the funding. That was about $7 billion to establish a packaging and prototyping facility, which has been selected for Arizona. Operation of that facility is a little bit up in the air right now. The second piece was a digital twin institute, what's known as Smart USA, and that was established, and they've already had 2 funding calls for that facility. And then the third component was a grants program to establish research and development around packaging in the United States, because it's not enough to make the chips. You also, how you package them, how you put them together is critically important as well. And then the fourth component was the program that I ran, which was the metrology program. This was to establish a large interdisciplinary research program at NIST around different areas where industry needed better measurements. So some people, if you've never heard of NIST, might say, well, why NIST? Why not NSF? Why not DOE? Why not DOD? And it turns out it's because NIST had a long history in doing research for industry. NIST is the only national lab whose primary mission is to support US industry, and a long history of working closely with the semiconductor industry around material science and engineering, electrical engineering, physics, packaging and test, and a lot of the other different aspects of research related to microelectronics. In fact, I started my own career at NIST doing laser metrology for the semiconductor industry. So that's one of the questions, is like, how do I get there, and what did I do with my physics degree working in the semiconductor industry, and how does NIST support this area? And often I get asked, how did you go from doing research to now leading this workforce development organization? Because the two don't necessarily seem related. And what I'll tell you is I've had sort of this squiggly career in STEM, and that's maybe my first piece of career advice for people to think about, is so often we think about titles, we think about linear lines, about how people move throughout their career, and a career is really a journey. It's not a ladder necessarily. And there's this great TED Talk, which Looks like the link got cut off on these slides. But there's this great TED talk around squiggly careers, and that's something I encourage people at the beginning of their career to think about, instead of focusing necessarily on just the next promotion. And so if you look at this ladder, you can say, how did she get from working in getting a bachelor's degree with an undergraduate degree in astrophysics, and then I got a PhD in nuclear physics, and then I did a postdoc in atomic physics. And then I ended up working at NIST on laser measurements for the semiconductor industry. Well, the thing that they all had in common was I liked tinkering. I spent a lot of time growing up as a kid fixing things, working on electronics, did a little bit of programming. And that was the thing that really got me excited more than understanding pion interactions in protons. It was like that was not the thing that filled my bucket every morning. And when they hired me at NIST, ironically, there were a lot of people who I had worked with professionally said, why did you take that job? Because on the surface, what I was going to be doing, what I was hired to do, was to calibrate laser detectors, which if you think about that, that sounds really boring, right? But what it ended up being was it turns out that the semiconductor industry was having a real hard time with their process development, and it's because they weren't measuring the laser power correctly. And so what I learned as I started to work on this problem was it wasn't so much that they needed calibrated detectors as that they needed to understand how measurements are made correctly. And so I would say that's my first thing, is sometimes when you get hired to do one job, on the surface it may not seem very interesting, but if you get to the root cause or the why of why they want you in that role, it can lead to some very interesting problems, which it did for me. And I ended up doing research on laser measurements for not just for the semiconductor industry. I got to work with some laser welders. I'll tell you a little bit about that in a minute. That was a lot of fun. Welding guys are really fun. I also worked with some medical doctors on better laser measurements for photodynamic therapy, which is a form of cancer treatment, which was very rewarding. And I worked with some test and measurement equipment with some folks at Keysight on better measurements for oscilloscopes. I'll tell you a little bit more about that also. And along the way, I kind of rose up sort of that management chain as well. I'm not really going to talk about that today because I don't think that's as much fun as to talk about the science behind these things. But the main thing was sort of a common thread was looking about how laser measurements are used in all of these different applications, which was a lot of fun. So you could say, what is important about laser measurements? One of the things is there are lots of different laser parameters. There's power, there's energy, is the laser continuous or pulsed? There's the angular distribution, there's the spatial uniformity, even the wavelength can matter for some applications. And so think of the laser as, if I'm a bit of a cooking nerd, think of it as like the flour. If you were going to make something, it's the ingredient that you're going into and you use it. The detector is kind of like your cup. How much flour are you going to use in the application that you're doing? Are you trying to make a cookie or are you trying to make a souffle? But the problem with detectors and laser detectors is that there are lots of different detector parameters. You might use one detector because you're interested in the pulse shape of the laser, but you might use another one because you care about the angular response, or you might care about the power level. So it turns out that choosing the right detector for the laser measurement that you're trying to make is really hard. But guess what? If you go into industry and you're in the testing group, you know what they're going to do to you? They're going to hand you a box of measurement equipment, and it may or may not be the right equipment. And so part of the first thing you have to do is decide and evaluate for yourself based on what is the flour that you're trying to use and what is the cup that you're given available, is whether or not you've even got the right one for the job. So it's about taking the knowledge that you've gained in your classes and having to apply it in a different setting. That can be one of the biggest challenges. So getting exposure to research opportunities at Boise State or at an REU or in graduate school is a great place where you can learn about all of those different applications and thinking outside of the box like that. Why should you care about laser measurements? It turns out there are a ton of laser applications out there. I mentioned some of the medical applications. Other ones include LASIK. Has anybody had LASIK? A couple of people. By the way, having worked with LASIK doctors, I would never have it done. Okay, just gonna say, but that's like a whole separate talk. People use lasers for communications. If you send an email, guess what? At some point, it's going over an optical fiber cable. It's used for sensing, like methane emissions from fracking sites, but it's also used for materials processing, welding, cutting, marking. It turns out that one of the most common laser applications out there is cutting fabric for clothes these days, believe it or not. And some of the very first laser safety measurements were around those optical scanners in grocery stores. But I mentioned there are lots of common laser measurement mistakes, and I've literally seen them all. And I could spend all day talking about all of them. But they all boil down to people using the right equipment, but the wrong method, the wrong equipment, or they don't know how to make repeatable measurements accurately. So these are all skills that as you're taking your classes or doing research for you to think about. But let's talk about like these two problems that I think are interesting, particularly for this group. The first one actually has a material science component, which is how do you measure laser power at kilowatt levels? Okay, think about it. This is enough laser power that you can melt steel. So what kind of a detector are you going to use to measure it? And to give you an idea about how complex this problem was when we were talking to these laser welding people, was that you're trying to measure a welding power and the fluence is 100 times higher than it is on the surface of the sun, at least. Okay. And so that's a really hard thing to do. And then the other thing that's hard to do is that it's in a really dirty environment. There can be up to 4 different states of matter present. You can have gas, liquid, solid, and plasma. And then it turns out when you're trying to do welding with a laser, those time scales are really important, whether you're looking at things on the nanosecond time scale or as you're doing a continuous weld on the second time scale and longer. And then the other challenge is looking at the welding properties at the different physical scales that are relevant. Everything from the full weld itself here, like you see in an automotive manufacturing center where they're doing something that's meters long, to also here, which you can't see as well. This is an electron microscopy image of a weld pool with the micro cracks in copper. So understanding the physical changes that are happening around the weld pool. So this is a very complex problem. And what we did, because we were working on this, is we had access to physicists, we had access to material scientists and mechanical engineers, and some people who are doing some computational modeling. And we all sat down and worked together to say, can we understand how changing the different power levels of the laser, changing the different temporal profile, maybe even changing the wavelength, could change the outcome of your weld. And along the way, the part that I worked on was trying to come up with a detector that could withstand 1 to 10 kilowatts of laser power. A traditional detector is converting the laser power to heat. The problem with that is if you have that level of intensity, you convert it to heat, you're going to melt your detector, right? So that's not going to work. There are other detectors, quantum detectors or photodiodes, and some of you may have used photodiodes. And the way a photodiode works is converting the photon energy to electrical energy. The problem is you'll melt the photodiode, so that doesn't work. So some people will pick off part of that energy and measure the photodiode. But guess what? The problem with these quantum detectors is they can be very nonlinear, which means that I can't reliably use that to measure laser power over a broad range. So those weren't going to work either. They also have damage and aging issues. So in the end, one of the guys in my lab had this really clever idea, which is, it turns out if you bounce something off a surface, that change in momentum exerts a force on that surface. Turns out if you bounce a kilowatt laser off a mirror, there's enough force there that you can measure that force. And so that's what we ended up doing. And it turns out, just to sort of give you like a ballpark, what are we talking about in terms of these forces, is for a 4 kilowatt laser, you're talking about 30 micronewtons, which is the equivalent about the weight of a paper clip on a scale. And that's something that we could measure, and it turns out it's very linear as well. And in the kind of goofy thing, which is a nice place about working at NIST, is when we came up with this crazy idea is we had a lab that had one of these lasers in it. And because we're at NIST, we had a whole bunch of scales. So we literally glued a mirror to a scale and we're able to measure a signal to do a proof of concept. And in the end, built a whole detector around that. And it's now actually sold as a commercial product out there for these multi-kilowatt lasers. And the other exciting thing about this sort of novel approach is you'll notice if you bounce the laser off of it, guess what? You can measure the laser power while you're welding, which turns out to be a very useful thing to do. The other thing that we did is I mentioned that we worked with material scientists, so we were able to do things with the Boulder Precision Imaging Facility where we could do correlative measurements across a series of microscopes from SEMs and TEMs to atom probe tomography tools. So that's kind of one example. My other favorite example is from the communications industry, and this is working around 10 gigabit transceivers. You may have remembered this in the, well, maybe you're not, you're too young. But in the early 2000s, people came out with these 10 gigabit transceivers, and initially they couldn't get them out in the market because the failure rate was too high to make them at scale. The false rejects, simply because they couldn't calibrate oscilloscopes correctly, was about $200 million a year. So a major manufacturer came to us at NIST and said, which of our oscilloscopes is right? Because this is the same transceiver measured on two different oscilloscopes. So we looked into it a little bit carefully, and what we discovered, and I want to spend a little bit of time about this, and you could say, why do we care about oscilloscopes? And one of the reasons we care is about oscilloscopes are really ubiquitous. I bet everybody in this room has used an oscilloscope. Is that right? Only one person has used this? No. About 200,000 US college students every year learn how to use an oscilloscope. And the way that this test works is you test a transceiver is you look at all the different transitions from a 1 bit to a 0 bit. And then you overlap them on top of each other. And if they overlap and they don't have any signals that cross into this forbidden region, then you say that your transceiver is passed, that it has enough signal fidelity that you can tell the difference between a 0 and a 1. But you can imagine that there are times where maybe the pulse is not quite that square shape that you were looking for. And if the pulse then goes into this forbidden region, it fails. And you could say, one of the issues with the way people were calibrating oscilloscopes at the time is, so here's that transition from a 0 to a 1, is both of these curves, one is sort of smooth and one has a little bit of noise on it, the blue curve, they both are very different. Can we all agree that they're different? Yes, okay. But guess what? They have the same rise time and they have the same amplitude. So at the time, from the way that people calibrated oscilloscopes, which was only to quote those two numbers, then you would say that this is fine, okay? But clearly it would pass one transceiver and it would fail the other one. It turns out the way that these oscilloscope works is, this is where you need to know a little bit about electrical engineering, is you have a source that that is impingent on that oscilloscope. The oscilloscope has some kind of a transfer function. It's got a channel that accepts it with impedance, and it's got a receiver that's going to measure that signal. And so the measured value, or this M, is really the convolution of the source, the channel, and the receiver. So it turns out you could have two oscilloscopes from the same manufacturer, and simply because the impedance is a little bit differently, or the receiver that they used in the oscilloscope was a little bit differently, you would get a different answer for that same gigabit transceiver. So at NIST, we developed a calibration method where instead of just looking at the rise time and the amplitude, it could characterize the whole waveform. So it could deconvolve what this channel and receiver was, so you could calibrate out the response of the oscilloscope to get back to the original response. Turns out is very difficult because this is a dynamic measurement. And so in this case, we worked with electrical engineers, we worked with physicists, we worked with statisticians and computer modelers to basically develop the tools that we could do that. And this is just sort of the spaghetti of all of the different traceability, starting with the calibrated photodiode that we could use and send to people as that calibrated source that they could use to calibrate their oscilloscopes in the field. Because there are so many oscilloscopes that need to be calibrated, having everybody send their oscilloscopes to NIST is just simply not a practical way in order to distribute these results. So giving them those sources and the code, we were able to let them calibrate out their own detectors. What was amazing about this project is this was so important that within 6 months of us finishing this, Keysight was offering calibration kits based on the technology that we had developed. And so for me personally, it was very satisfying to see how many people cared and how quickly it could be disseminated widely. So we talked a little bit about the CHIPS and Science Act, the EDGE program, interdisciplinary nature of trying to solve these problems. A lot of the problems that are addressed in industry, the really hard ones, are ones that aren't in a textbook. You need to be thinking about all the different components and the different kind of competencies that you need in order to solve these problems. So where do we go from here? And this is where you get my little bit of career advice, and I think we're still on time. Often I get asked, what should I major in? How did you get keys to your success? And I think it's really two things. One is this real world experience, and one is having some self-awareness about things that I'm good at and things that I'm not so good at. And believe it or not, I've had real world experience as a waitress, receptionist, dog walker, housekeeper. All of those have been, I would say, important at some point to my success. Actually, having a clean lab is really important if you want to do repeatable measurements, believe it or not. I had a lot on the job research experience. I worked in a chemistry lab. I've done research in particle physics, nuclear physics. I taught at the University of Colorado for a semester. That's not something I'm very good at, just full disclosure. And then I've had different roles on project teams, and it was good to catch up with students over lunch and to hear about some of the things that they're doing around getting some of these experiences as well, because I really do think that they're helpful to setting you up to succeed, to finding a career that's a good fit for what you want to do. In terms of self-awareness, having some ideas, what are the things that you care about? What are the things that make you excited? So somebody mentioned at lunch that they had taken the strengths inventory. That's one really good tool that I encourage people to do. And then another one is the strong interest inventory, which helps you identify how you like to work in your work styles and how it aligns to different career options that are out there. For me, taking those kind of assessments was really helpful at one point, because at about in the middle of my career, I was a group leader. I was supervising this enormous group of about 30 people, and I was not having a lot of fun. And I was actually thinking about doing something completely different. And what it helped me realize is to identify the parts of my job that I really enjoyed, the parts of my job that I did not enjoy, chasing people down for their timesheets, for example, and to delegate the things that I didn't enjoy because they could be career development opportunities for somebody else. It actually helped me reinvent my job. So even though I didn't change my title, I changed the approach to how I work. I would actually say, even for faculty, that's a good thing to do because reinventing yourself or in your career from time to time is a good opportunity to stay excited about what you're doing every day. The interesting thing that I learned from taking that strong interest inventory is I care more about I have my own internal metrics for success. So jobs where where somebody else was evaluating whether or not I had met a success goal is like not a good fit for my work style. And I don't like to do the same thing every day. So I need a job where I can be sort of a creative thinker and take new approaches to things. And I'm very collaborative. So I like to work with other people. So working in the EDGE consortium, for example, is a great opportunity for me. But once you've done that, so I encourage you to take some of these career interest activities, and you have access either through your department, it sounds like, and also through the career services, is also to reach out to your near peers to learn about their careers and their career journeys. Another thing is hosting a near peer mentoring event. And again, talking to the students at lunch, it sounds like those are activities that are going on here today. And from the speaker who was before me, I encourage you to take advantage of those if you haven't. I mentioned the strong interest inventory and the Clifton Strength Finder. I also encourage students, if you're not quite sure about graduate school, is to consider taking a gap year or doing a post-baccalaureate program. At NIST, we have a post-baccalaureate program where students with just a bachelor's degree can come and work in a lab for a couple of years, gain some real research experience, and then think about what they want to do next. It's been very successful in helping people pivot if they get their degree in one discipline and decide that they really are interested in something else. The other thing is to get that real experience. So how to get a job or internship. It sounds like you've got great advice going on. Like here are just some other suggestions to think about. When I was making a change going from nuclear physics, you could say going from nuclear physics to work in the semiconductor industry, I didn't do it overnight. There were a lot of intermediate steps. And my first step was actually going from a PhD program in nuclear physics and getting a postdoc in atomic physics. And what I did was simply, I contacted a lot of people and I did a lot of informational interviews. And I managed to find an atomic physics group who needed somebody with electronics experience and with doing computer modeling. And so the skills that I brought to their lab were things that they needed, and I got to learn about how to take apart and fix lasers, which led to my next job. I probably called or sent emails to well over 500 people in that process. And a lot of people didn't respond. But at the end of the day, you only need a handful of people to respond. And I think today people are even more open to informational interviews than they were when I was going through that process. And through EDGE, that's one of the things where if there is a particular interest for a particular student, I am more than happy to leverage my professional network to hook you up with somebody whose interests might align with career opportunities that you're interested in. The other one is usajobs.gov. If you are a permanent citizen, if you're a citizen or a permanent resident, you can apply for, and they have jobs set aside specifically for people who are within 2 years of their degree. And that's a great opportunity to try something new as well, and to try a career in public service if that's of interest. I also encourage graduate students to consider the NSF intern program. This is an opportunity to do a non-academic internship while you're in graduate school. And if your advisor has an NSF funding, they can apply for supplemental funding to participate in that program. And then finally, there are always the Career Services Office at your university and participating in EDGE programming to learn more about some of the industry speakers that we're bringing in. In terms of applying for a job, There's a resume, a cover letter. Never forget the cover letter. It's really critically important. And then I always encourage students to have an elevator speech available, at least internally. Why are you applying for this job versus all the other jobs? And I know that a lot of people use ChatGPT to write cover letters right now. As somebody who's read a lot of applications from a lot of students, I can usually put them into two piles. A pile of students who only use ChatGPT to develop their cover letters and resumes, and ones who at least put a little bit of thought and did a little bit of homework in advance. So I'm not saying don't use ChatGPT. I'm a big fan of Grammarly, for example, but do it with some foresight. Put in your own interests. Have a why. If you can't get to the why that you're applying for a job, then maybe you shouldn't apply for it. And then I'm going to go back to this. The competency model that we talked about earlier can help you with that why. And as you're crafting your cover letter to say why you for that job, think beyond just your academic qualifications and the competencies that you've learned in your program. Think about competencies you gained maybe in problem solving, maybe in project management, maybe in team building, maybe in being a mentor through some extracurricular program that you've done that you should be bringing into that cover letter, because all of those skills are things that people are looking for in industry. And then finally, navigating those career transitions from being that team player at the beginning of your career to moving towards an independent contributor to finally hitting project teams. This is where you're going to be reinventing yourself throughout your career. I get a lot of students sometimes who will think about they'll talk themselves out of applying for a job because they don't think they have the qualifications, or they're not an exact perfect fit for the job description. Maybe the job ad says that they need an electrical engineer and you're a physics major. Maybe it says they want a mechanical engineer and you're a material science degree. Going a little bit deeper and reading the description, if it's something that excites you, don't let necessarily that degree stop you from putting yourself in there, because most of these entry-level jobs, it's not just based on the degree, but again, some of those other competencies that they're looking for as well, sort of the whole package. And that's the thing to remember as you're starting out earlier in your career. As you get to that independent contributor, don't forget to sort of reassess where you are and how what's your personal vision statement in terms of what is the career that you want for in your life. My personal vision statement was, I want to use my sort of physics experience to work on really interesting research problems. And I wanted to live in Boulder, Colorado with my family. So that sort of were always, as I was considering different job opportunities, those were the two things that I used for decision-making purposes. And then I guess finally, get involved with EDGE, because this is a way for you to become more familiar with those opportunities outside of the Boise State community. This is an opportunity to become aware of some national level efforts, and potentially visit some of these companies and learn from other students at other universities. For faculty, we're looking for faculty to get more involved. We'd really like you to share your internship opportunities with EDGE scholars if you're looking for students, potentially give a virtual seminar to our students. And there are workforce development proposals out there. If you've got an idea for a workforce solution and you're looking for a national cohort of students to evaluate how effective this solution is at scale, then we'd like to collaborate with you. So to kind of close up, EDGE is fostering this national effort to promote transparency and learning opportunities and empower students to take advantage of these career progressions. And collaboration is really required to meet the needs of the future semiconductor workforce, because we need all STEM disciplines. I'm going to paraphrase Lisa Sue, who's one of the people that I admire in this industry, is that for us to come up with good workforce solutions and for us to prepare students and to help our alumni navigate the transitions of their careers later on in this industry, we need to work together because no one organization by itself has all of the answers. And I guess our interest forms got cut off, but that's okay because Boise State is already a member. And I want to make sure to acknowledge here that this work is a lot of work. It was not done alone or in a vacuum. I've got some really excellent collaborators at Dartmouth, Tennessee, Indiana University, and across these EDGE schools. Ann Kiramonte DeBay, John Lehman, Bryman Science, and Paul Williams at NIST worked with me on the laser work that I shared with, and Tashi Dennis, Ari Feldman, Paul Hale, Jeff Jargon, and Dylan Williams collaborated with me on the oscilloscope work. So I want to make sure to acknowledge them because science is truly a team sport, I like to say. And with that, I want to just sort of thank you, and we look forward to collaborating with you. There's my email address if you want to follow up with me on anything in particular. And I think happy to answer any questions.
All right. I'm a computer engineering major. I just transferred here from a different university in Wisconsin. And I was curious, is semiconductors, because I know kind of electrical and computer really stick together there. Would the Chips and Sciences Act really benefit myself to be looking into the semiconductor base as something for a future?
Absolutely. Yeah, absolutely. Absolutely. And I guess I forgot to give one of my favorite anecdotes was whenever I'm at these semiconductor industry events, my favorite question to ask them is what degrees or how many double E's are there? So I was at a semi event with 12 senior people sitting at a table, and I said, how many double E degrees? And guess how many people raised their hand? Just one. Okay. There was mathematician, computer science, computer programming, computer engineer, chemistry, physics, biology, economics. I mean, they were all over the map because this industry needs people with lots of different backgrounds. In fact, I'm not sure if Ira's here today, but I met with him earlier today. He used to be at Micron, and I think his background was in computer programming or math, but he ended up working in hardware test. The important parts about the degree that you're learning is, are you learning how to solve problems? I think you probably are. Are you getting some hands-on experience? And is it relevant to what this industry needs? And the nice thing about, again, being at a place like Boise State is you're very close to a lot of different sort of out of the classroom experiences that you can take advantage of. And I've had a lot of fun working in this industry. The main thing I think I want to say to you is just because your degree isn't in electrical engineering or one of the ones that's on that job ad, don't rule yourself out. And like at a minimum, you could ask for an informational interview with somebody at that company and say, do you have people with a material science degree at your company and what do they do? And I think there is, I'm looking to Amy, I think there's an event that's where you bring industry folks onto campus where you can ask them exactly those kind of questions. And so I would really take advantage of those opportunities as well.
The correct answer is to switch to MSc.
Well, that's my husband, the material scientist, would say that also. Because there are so many interesting problems in material science.
Thank you for the talk, Marla. This isn't really a question to you. It's more of a question to all the students in here.
Yeah.
Has every student here met Leandra yet? Okay, if you don't know who Leandra is, you better figure out who it is because she's the one that helps you get jobs. That's her entire job on campus for us of College of Engineering students. So please make sure to talk to her. She'll help you set up resumes, cover letters, how to find jobs, all the fun stuff.
Yeah, and talk to her. Don't wait until you're looking for a job or need a job. Talk to her now.
Yeah, Hector and Jolie, go talk to her.
Because the other thing that we were talking to at lunch is that there's this Micron MSc educational MERC That's right. I met with some of the people from the Merck program. You know, that's a great opportunity to get experience outside of your classroom on how to be a better public speaker, a better one than me, certainly. And then also how to talk to people about what you're doing who are not experts in your area, how to organize other people to do that. So those are also some opportunities for you to gain some of those competencies that industry is looking for that are outside of your normal classroom experiences.
For some of those links that got cut off, we'll send an email so you can get access to those industry interest forums and the school interest forums. This will also be up on YouTube if you want to rewatch that. And then we'll also include all of the links that you saw today too. Thanks, everybody.